gas and dust together, if you make a big enough clump of gas, the pressures rise to the point where you can stimulate fusion in the center of that gas, and that's a star. Yes, sir?
I wonder if you can expand maybe on the ground-based observatories, because since roughly 1990, the progress on making bigger and bigger ones has really exploded.
Yes.
There's the Giant Magellan Telescope,
right,
which I know a little about, and there's this really big one in Hawaii that may or may not.
Maybe, yes. Yes, so we have a whole segment. I don't think it's today, but we do have a whole segment on ground-based telescopes.
Okay.
In this.
But that arrow that you have right there going to about 6 billion years,
yeah.
Is that before any of these current big ones came online?
No, they're still limited by the atmosphere. There are a lot of improvements that we will discuss when I talk about ground-based telescopes. But the space-based telescopes give you a chance to look farther. And the reason is, even if you correct for the shimmering of the atmosphere is not transparent in the wavelengths that let you look farther back. You have to go to longer wavelengths in the atmosphere. Moisture in the atmosphere is the limiting factor. That's one of the reasons they put telescopes on the top of mountains. Not only there's just less atmosphere to look through, less shimmering, twinkling, and so forth, but also there's much less water vapor. So that's, but we have a segment on ground-based telescopes. I don't know if it's today. Okay, so if we're talking about the early universe, let's reiterate what we mean by early. 0 to 380,000 years, a whole lot of important stuff happened. We inherit what happened in that interval, and then nothing happens for a long time. 400 million years before we get stars. And then things get interesting again, and we do, surprisingly, know a lot about what happened in the very early universe, the first few seconds, in fact. We have, I make this statement with some confidence, we have better ideas about the time from 0, or a billionth of a second, forward. That comes from what we know about particle physics. They study at places like the big accelerator in Switzerland, in France. Okay, so let's keep going. So here's another picture. I know you can't read this, but there's part of this I want you to see. So I've broken this up into pieces. This is another history of the universe, starting from the very earliest time, which is time so short they make no sense to us. 10 to the minus 41 seconds. And this goes forward. So I've expanded this. Now maybe, I hope for the people in the back this is readable. That says 10 to the minus 41. And so these are eras in the evolution of the laws of physics that dictated how the universe evolved. This is our theory of how this happened. So we have the Planck era, named after a famous scientist from 100 years ago. Then we have this era where all the forces in nature that we know about all existed as a same force. That is, there was not a separate gravity, electromagnetic, weak force, and so forth. They were all one thing. And in the early universe, those forces became separate and distinct. But our best understanding of the early universe is to assume that there was a single force at work. We don't understand that force very well, but it's a theoretical foundation that people use. And now, what I've done here is this drawing, which goes top to bottom, has been reproduced. So as we go down this panel, we're going forward in time. At this point, we're still at 10 to the minus 10th seconds, and the temperature is 10 to the 15th Kelvin. So it's pretty warm. And then here's the bottom half of this drawing, where we now get particles, and then we get nuclei, and right there it says 5 minutes. So when I say that a lot happened in a very early universe, the first few minutes everything that dictates how we see the distribution of galaxies today happened in that interval, in roughly 5 minutes. This reminds me of a book you might want to read. It's a little technical, no equations, but a little more advanced. Steven Weinberg's a book called The First 3 Minutes. So if you're a little more ambitious, you might want to take a look at that book. You could probably buy a copy for $3 on eBay because it was first published in 1985 or something, so 35 years old. But the first 3 to 5 minutes is really important, and we will continue working on this issue. So here, unfortunately, another backwards drawing from our friends. This is 10 to the minus 43. That's the earliest sensible time we have in the universe. And going to the left, time is getting long, and we're going toward us. And you see, this is this force that nobody understands real well, where everything was the same, interacting with primitive particles in the early universe. And then gradually these things split into 4 different forces that we observe now. We understand gravity. We understand and exploit electromagnetism every day. That's how we get radio signals and cell phones and all that. The strong force is a thing we don't experience. That has to do with nuclear physics. The weak force has to do with radioactive decay. But we interact with electromagnetism and gravity every day. But the theory is, originally, all this stuff was part of some mysterious early force. So to make this left to right sensible, I flipped this drawing over as well. So early time on the left, later time on the right. Okay? Here's another one, a nice piece of artwork, but once again, the Big Bang is on the right, time goes to the left. But you see the same structure here. This orange panel represents the first 380,000 years where there were no particles. It was just a soup of pieces. And then it cooled enough that we have the dark age. And then stars, galaxies, and human life. Right? Question, yes?
Yeah, and it may sound really stupid, I don't know. Is it possible for something that's like, let's say, 12 billion years old to be more in the center of, the universe?
Oh, well, understand, everything we know about the universe involves using a time machine called a telescope. When we look at ancient stars, we're seeing them as they were when the light was produced. 12 billion years ago, for example. That star, or that galaxy the light came from, is no longer there, or it looks dramatically different. We have no way of knowing. We have to wait for that light to propagate to us.
So when we're looking at the center of the universe, we're looking at that distance in time.
Right.
And we don't know when that was formed, though, or we don't know how long it's actually been there.
No, we know how far away it is.
Okay.
But keeping in mind, the whole time that light's been propagating to us, the universe has been expanding. So right now, our measure, it's called the look-back time. So this is good you asked this question because this is fairly technical. I mean, if you watch the Discovery Channel, you can find a show about the universe. They're not going to get into where we are now. The look-back time is how far away that source would be if we could see the whole universe as a snapshot. In reality, we can never do that because our attempt to look back has to take into account how long it takes the light to get to us. In that interval, the universe has changed its size.
So the universe can be much, there's a lot of the universe we may not ever be able to see.
Well, yes, and I don't know, I'll say something, you tell me if I said it last week. 13.7 billion years is the size of the universe that is accepted right now. The actual universe, not the universe we are observable to us, but the actual size of the universe is probably about 45 billion light years. It's much bigger than what we can see because the expansion rate when it was born was dramatically bigger than it is right now. So it's had this huge expansion, and the expansion has continued for the most distant parts of the universe.
That's called inflation.
As the result of inflation, the expansion in the very earliest part of the universe was astonishingly huge. I didn't mention it, but it's in all these drawings. Let me show you. Expansion, as it's right there. Here, I'm going to walk into the picture for this a little bit. There's a single point right there, smaller than an atom. That's the beginning. And then it jumped in an instant to this huge size. That's part of the theory of inflation. We will talk about inflation. It's a radical idea, but it has been proven right over and over again. And we'll get into that. Unfortunately, the guy who invented it, Alan Guth, probably will not ever win a Nobel Prize, because Nobel Prizes are reserved for scientists who predicted something that is observed. We right now do not think there's any way to observe any kind of fingerprint from that inflationary period. Here's another drawing of the same thing. The universe starts right there, and then you see the word inflation here. An explosion in the size of the universe in a tiny fraction of a second, and once again, we get cooling, dark ages, and we get collections of stars, clusters of galaxies, and so forth. Yes?
So what you're saying is that people are accepting the 13.77 million years because it's observable.
Yes.
But in actuality, it really is about 45 billion, but we can't.
Okay, sorry, I have to interrupt.
Okay.
The universe age, we think we have that right.
Okay.
When I said 45, I'm talking about the size. 45 billion light years in size in 13.7 billion years. So now a question you might ask is, well, how does something get bigger than the speed of light would allow you to calculate? And the answer is, this is the expansion of space. It's not limited by the speed of light. The speed of light limits your velocity through space, but it does not limit the rate at which space can increase in size. So we'll talk about this again. Now, Einstein showed us that the velocity of objects moving through space is limited to the speed of light, but that does not restrict how fast space can expand. So there's no contradiction there. All right, so we've talked about this several times now, so I think I've made my point. There's two key times, 380,000 and 400 million. So in the very early universe, prior to 300,000 years, that's this boundary right here, just pieces of atoms flying around, and you see the temperatures, 6,000 Kelvin, that's the temperature of the sun. The average temperature of the sun is about 6,000 Kelvin. And the early universe was at about the same temperature. When you get to 3,000 Kelvin, then these pieces can start forming atoms. And that happened at around 380,000 years. And going forward from there, you have atoms that find each other and collect into clouds, and the clouds become stars, and groups of stars become galaxies. So now let's talk about nucleosynthesis. I have to ask my girlfriend for a tissue. You have a tissue in there? I'll come back while you're doing it. So we have BBN. That's the abbreviation we'll use for Big Bang nucleosynthesis. Thank you. Sorry. Everybody now has a ruptured eardrum. My apologies. Okay, so I want to introduce, now we're going to talk in detail about what went on in that first 380,000 years, and in fact, what happened in the first 10 minutes or so. We understand this extremely well. I'll show you why we have evidence of that. There were a few gaps in our knowledge, but what we know very well. Okay, so BBN is an abbreviation I will use. So let's look at the distribution in the universe of various elements you would find if you think back to your days taking chemistry. So we go to the left here, and right up there at the top is H for hydrogen, and then helium, lithium, beryllium, boron, carbon, and so forth. This zigzag pattern here is very interesting. It has to do with how nature builds the nuclei of atoms. You can take a proton and add a neutron, and you have deuterium. And if you add another neutron and another proton, you have helium, and so forth. And the right number of electrons will show up to surround that nucleus and build atoms. So this we get from astronomical measurements. By looking at galaxies, we can do a census of the amount of different materials that exist in different galaxies, and then add that all together, have a graduate student take billions of galaxies, how much hydrogen and lithium and boron is in each galaxy, and aggregate that. And this is what we get for the abundance of atoms from the periodic table of chemistry. This is how it looks. There are fewer heavier atoms, more light ones. Beryllium is a kind of an odd, this little community here, a little bit odd. We'll talk about that. Okay? Now, comes some interesting history. George Gamow, who became world renowned by writing science books for the